Thank you guys for having me. It's always a pleasure to get to speak to and interact with young people who are interested in technology. And it really doesn't feel like it was that long ago that I was sitting kind of metaphorically where you all are sitting as a sophomore or junior in high school. But it turns out that was, as I'm going to discuss a little bit as we go through this talk, about 25 years ago. So I do want to reflect a little bit on what the last 25 years have changed in technology, and then kind of project a little bit into the future about what that might mean for you guys as you're coming up in this field. So to tell you just a little bit about myself, I started working in IT in some capacity in 1996, so about 25 years ago, at a small internet service provider in Mississippi. So I worked in tech support, did a lot of hardware, building computers and setting up networks, things like that. A little bit of freelance development as I worked my way through college. So that was all kind of my high school and college life. Eventually graduated from college, went out to work in the real world doing IT and information systems work for international paper, then First Tennessee Bank, but spent most of my career working at the Bank of New York Mellon. We actually had a large data center facility in Nashville, Tennessee. So interestingly, all the processing for the Bank of New York was happening in Nashville or Pittsburgh, or a little bit was going on in Teaneck and Somerset, New Jersey. So that was kind of the bulk of my career. And then in 2011, I decided I wanted to try being a professor and go back into this academic lifestyle. So in 2011, I went to the University of Arizona and did my PhD in information systems there. Graduated in 2015 and have been a professor here at the University of Houston ever since. So I don't know if I've seen it all, but I have seen a lot of different aspects of information systems, from being very kind of low-level telephone tech support and troubleshooting people's hardware failures, to working with very large enterprises where we have servers and network equipment that cost hundreds of thousands of dollars. And I do quite a bit of consulting on like cloud projects now, and teaching the undergrad, masters, and PhD space. So kind of have a wide range of exposures here that I'm happy to share with you, and happy to answer any questions you all might have. So I'm not sure how well our bi-directional communication is going to be working, but if you do have any questions along the way, feel free to stop me or send word to Jonathan, and he can stop me and either ask a question aloud, or I can even pull up our chat window here and I could accept questions and things that way, or we can just have some discussion at the end, whatever makes the most sense. But I wanted to start our conversation today by bringing up a quote that we see often used in like introduction to information systems or introduction to business computing classes. And it seems at its face like a really silly quote. And this is from the CEO of IBM in 1953, that I think there's a world market for maybe 5 computers. Right. And this seems absurd now, right? Because I have, I think, maybe 5 computers in my office right now. Right? I've got my desktop that I'm presenting from. I have my laptop here. My smartphone is a computer. My tablet is a computer. There's billions of computers in the world, right? 5. This is kind of used often as an example of how bad we can be at predicting what the future is going to look like. But I'm actually going to challenge the notion that this was really that awful of a prediction, right? Because we have to understand in 1953, it was a very different world as far as computing went. Like, these were the computers that Thomas Watson was talking about, these giant machines that filled up an entire room. And these big boxes here are basically the equivalent of your hard drive. And then there are processing units all around the room. And then you had people sitting at terminals to interact with these giant machines, right? So you didn't actually sit at the computer like you would sit at your laptop or a desktop computer, or just hold your tablet in your hand. The computer was elsewhere in the room. And then there was just a screen and a keyboard and a printer that was connected to this giant computer. And there were probably many, or at least several, keyboards and screens and printers hooked up so that multiple people could interact with this big computer all at once, right? And in this situation here, you've got, this guy's typing out something and getting some printed output from the computer. She's loading in some type of data or application on some magnetic tape that the computer is going to be able to read. So it's a very different situation of computing that we were looking at in the 50s and 60s and even into the 70s. And I mentioned that that's computer, and my phone, we could consider that a computer. And so I think to really set the stage for this, we need to consider, what actually is a computer. Let's come to a common definition on that. And there's really four basic components that make up what we would consider a computer. We have some type of persistent storage, like a hard disk drive or a solid state drive or some type of flash memory. We have to have something that enables the computer to persistently store some data, right? Otherwise, every time you booted up your computer, you would just be at nothing, right? Your computer has to store like the operating system, right? And your applications and your data for it to really be useful. So there's some type of persistent storage. We also have some type of much faster storage, which we typically refer to as memory or random access memory. Okay, and this is volatile. This is non-persistent in nature. So anytime we turn off our computer, we're going to lose everything that is stored in memory. Okay, the plus side is it's much, much faster, right? But also much more expensive. And again, it's volatile. So you might be familiar with having something like 500 gigabytes of hard disk space, but only 16 gigabytes of memory, right? Or maybe you've got 1,000 gigabytes of disk space and 64 gig of memory if you've got a really nice machine. But at any rate, you're going to have typically much more persistent storage than you do memory. Okay, so persistent storage, memory, some type of processing unit, typically a CPU or a GPU, right, to actually execute on instructions. And this works hand in hand with your memory. And then finally, we have input and output devices. So the kind of most simple, straightforward, your KVM or keyboard, video, and mouse, but also things like touchscreens are both an input and an output device, speakers, microphones, printers, all of these things. But what we're going to talk about most today, and the thing that's going to have the most impact on your performance, is your network, right? Where you get data coming in and out of your computer, right? So we've got persistent storage, memory processing, and I/O, which we're going to operationalize today as your network interface. All right, so back to 1996, when I first started working in IT, I was working at an internet service provider in Fulton, Mississippi, which was kind of joined with a computer store, like a hardware store. And back in 96, the way of purchasing a computer was typically not to go to Dell or to go to IBM or to go to HP or something like that to buy your personal computer. Often the way you would do this was find your local computer store and tell them what you want, and they would custom build a computer for you. So this store that I worked at, internet provider and a computer store, and we had a inventory of cases and motherboards and memory and hard disks and things like that. And we would just custom build these computers that people would order. So once I started working there, got a little bit of spending money in my pocket and got a nice employee discount. And I wanted to build myself a computer for doing all the stuff I wanted to do, primarily playing Quake and Doom and all of these, mid to late 90s games. So I built a really nice computer for myself, which had a 2.5 gigabyte hard drive, right? My phone now has 100 times more storage capacity than that. but my computer in 1996, a 2.5 gigabyte hard drive, 16 megabytes, not gigabytes, but 16 megabytes of memory, a 200 megahertz CPU, and this is just single core, single threaded, nothing special about it, just one individual 200 megahertz CPU, no GPU. GPUs, separate GPUs were not a thing back in the day. And my internet connectivity was a 56K dial-up connection. It was amazing at the time, but clicking on a web page or getting anything, it would take 30 seconds or a minute or several minutes to load just a simple web page. So a very different environment than what we're used to today. And this isn't a picture of my actual computer, but it looked quite a bit like this. It was a beige box with some speakers and CRT monitor. And I think this is even running Windows 95 if I'm looking at this right. So this was my computer in 1996. So how do we get from 1996 to 2021? How have things progressed? One way of looking at this is by thinking about Moore's law. And when I was talking to Jonathan about this earlier, he was familiar with Moore's law, and many of you may be, but Gordon Moore was one of the co-founders of Intel. And what he said way back in 1965, so some almost 60 years ago now, is that the number of transistors in an integrated circuit doubles just about every 2 years, right? He's speaking about the density of how tightly we can pack things onto a silicon chip, okay? He's not necessarily talking about performance, right? He's not really talking about CPU speed or network throughput or anything like that. It's just how dense we can make these chips. And this saying has been kind of roughly repurposed into a lot of different operationalizations, but it is generally held pretty true that overall computer performance doubles every 2 years. And this isn't a law like a law of physics. This is just kind of a guideline for understanding how we might expect computing to evolve. So based on Moore's law, in 25 years, if technology doubles, if speed and performance and power doubles about every 2 years, we would expect that it's doubled 12 times-ish in the past 25 years, right? So doubling once is 2, doubling twice is 4, doubling 3 times is 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096. Would be if we doubled 12 times, right? This is 2 to the 12th. And as I was rattling through these numbers, I'd just like to point out that this is why you see these numbers come up over and over again in computing. You always have something like 8 or 16 or 32 or 64 gig of memory, right? You don't typically see 20 gig of memory, right? Or 50 gig of memory. So this is why we have these weird numbers pop up time and time and time again, is because with the binary nature of computing, it's all these exponents of or factors of 2, right? So with our 12 doublings, we would expect that computers now should be about 4,096 times bigger, better, faster than they were back in 1996. So we can test out this math pretty easily by looking at my computer from 25 years ago compared to what is available today. So 2.5 gigabytes times 4,096 is 10,240 gigabytes, which is about 10 terabytes. And that's a lot of storage. That's a lot of storage to put in a machine. But if you go Google or if you go look on Amazon right now, you can find a bunch of 10 to 12 terabyte hard drives for about $200, right? Getting 10 terabytes of storage into your system, really very accessible these days. 16 megabytes of memory times 4,096 works out to 64 gigabytes of memory, which coincidentally is exactly the amount of memory I have in this computer that I am presenting from right now. So 64 gig of memory, CPU, 200 megahertz times 4,096. This one we have to take with a little bit of a grain of salt because CPU performance is about more than just clock speed. Okay, so there have been a lot of other advancements in multiple cores and multiple threads per core, caching, offloading to GPUs, things like that. So I think we would find that CPU performance or processing performance is about 4,000 times what it previously was, but it's just in different ways than this raw number would indicate. And then finally, with our network speed, home network speed, business networks are a whole different story, but home network speed, 56 kilobits per second times 4,096 works out to 229,000 kilobits per second, or about 200 megabits per second, which is pretty typical for a cable modem connection through Comcast, Xfinity, AT&T, Cox, whoever it is you're with. And in fact, my home network speed is 600 megabits per second. So that's about 12,000 times faster than what we had in 1996. And you can easily get gigabit internet speed at your house, which would be about 20,000 times faster than what we had available in 1996. Amazingly different. Moore's Law still holding up some 60 years later. So I think we can say computers today are about 4,000 times better, by all of these different metrics than they were 25 years ago, right? And this increase in performance has enabled all kinds of different applications, all kinds of different use cases that we just could not have even imagined back in the mid to late 90s, right? So to operationalize what a 4,000-fold increase looks like, something that takes 10 seconds today, right? If you click on something and it takes 10 seconds to download, that would have been 11 hours back in 1996. Or if there's something that takes 1 minute, and 1 minute's a long time for you to wait on something to load, right? If you're starting to stream a Netflix movie and it takes a minute to load up, that would be 3 days that would take back in 1996, right? And no one's waiting 3 days on something or even 11 hours on something to happen. So we just didn't do those types of things back in 1996, right? Because of the computing power, we just have a completely different set of applications and expectations for our computing, right? So there was no YouTube, no Netflix, no Zoom. We couldn't do what we're doing right now, this idea of streaming HD video, like that was absolutely absurd back in 96. I did have a camera, but it was a black and white, like grainy camera, and we would get maybe 15 frames per second on a good day. And the interface for using it also very clunky, not elegant like what we have today, right? No Fortnite, no TikTok, no smartphones, tablets, Internet of Things, or even this idea of always on internet connectivity, right? In order to get on the internet, I had to very purposefully go sit down at my computer, of which there was one in the house, and this was kind of typical, and connect. I had to do the dial-up thing. My computer was hooked up to the phone line, and to connect to the internet, there were all these high-pitched squeals and screeches and static and clicks and pops to indicate these computers were talking to one another. Then I used the internet for a while. I checked my email, I loaded a website, I did whatever, and then I disconnected it, right? And then my computer wasn't on the internet anymore, right? This thing is always on the internet, and it's always collecting data and generating data. Very interesting situation. But for any of these technologies to exist, they all depend on other technologies having been developed, right? Because there really wouldn't be a YouTube unless we had smartphones, right? Because a lot of the purpose of YouTube, a lot of the content on YouTube is developed because now everyone has this high definition camera in their pocket that they can record videos and upload them to YouTube. But we wouldn't have these smartphones if we hadn't developed all these wireless internet technologies. And also if we hadn't developed these nice high definition LCD screens. That was actually one of the big enablers of the smartphone revolution was the creation of high quality, durable LCD screens, right? As opposed to like the little 1 inch by 1 inch squares, they got bigger and bigger and more usable, and the capacitive touch screens got better. So that enabled this technology, which enabled something like YouTube. When YouTube comes along, now all of a sudden people are wanting to stream video over the internet. So that really drove the adoption of broadband internet. Oh, and now that we've got broadband internet and people are streaming YouTube, why don't we just put full movies on the internet and let people stream that, right? There would be no Netflix if there had not been broadband internet, and wouldn't be broadband internet if there hadn't been YouTube, wouldn't be YouTube if there hadn't been cell phones. All these technologies enable new innovations. And as new applications push our technology kind of past their limits, we develop new technologies to enable those applications, which opens up a whole new range of possibilities. So it's a really interesting situation, I think. Looking back over the past 25 years, I think is a really interesting story, but I don't think it's the important story here, right? Because this is just an old man now rambling about what things used to be back in the day and how amazing things are today. What the really important thing for you all is, because in 25 years from now, in 2046, you'll be about my age, right? You'll be well into your career. So the question here is, what will IT look like 25 years from today when computers are 4,000 times faster and more capable than they are today, right? Assuming Moore's law holds up, which it has for 60 or so years. Wow, that gets us into a situation like we can't even imagine what the applications might look like when we have effectively infinite storage and effectively instantaneous network connectivity and processing capabilities, right? Now, our applications are going to grow and become more complex, and data will grow. There's going to be a lot more demands on that, but it's a pretty amazing thing to think about how primitive today's technology will look in 25 years, just like the technology from 25 years ago looks fairly primitive today, right? And to put this into a little bit of numerical context, if we said this is what a system today looks like, 10 terabytes of storage and 64 gigabytes of memory and a 600 meg internet connection, that would be 40 petabytes of storage, right? Many companies, like whole organizations, corporations, are barely talking about petabytes of data, 256 terabytes of memory in a system, and network speed looking at upwards of 2 terabits per second. That's incredibly big and incredibly fast, and opens up a whole nother world of possibilities. And thinking about some very clunky emerging technologies that I've used over the past couple of years. You guys may have been watching technology long enough to have seen when Google Glass was introduced. And it was kind of like, it looked like a pair of glasses, but it had a little screen sticking out right here in front of your face. This was maybe 2014 or so. And the lab that I was working with at the University of Arizona, we had one of these to, try to figure out if there were any interesting research questions that we could address with it. And it was terrible. It was terrible. It was hot. It had a little CPU here that got hot against your head. It was clunky. It was slow. The interface was a little weird, but definitely not usable in a day-to-day sense. But that's not really what it was intended to do. It was a prototype to help people understand, like, what might we do with the technology that looks like this, right? And when we get 4,000 or even 2,000 or 1,000 times more powerful and smaller computers than what we have today, that technology embedded into a contact lens, right? Or some type of wearable device, or if you believe some of the stuff that like Elon Musk is doing with Neuralink, things that are directly interfacing with your brain, right? If you've got a 2 terabit per second brain-to-brain connection with someone else, or a brain-to-computer interface. Like, we don't even really know what that type of thing would look like right now, because those technologies are so far beyond the capabilities that we have now. So it's really, really interesting to think about not just what the last 25 years have brought, but what the next 25 years may bring. So what's the progression to getting there look like? And I don't know that I'm going to be carrying around a phone with 40 petabytes of data on it in my pocket, because we're kind of shifting the way we're thinking about computing. And this is where I want to circle back to this idea that there's a world market for maybe 5 computers. This may sound even more absurd now at this point in my talk, right? A world market for maybe 5 computers. So recall, this is the computer we're talking about, where we have a big centralized thing with a bunch of terminals connected to it, right? Basically a bunch of screens, kind of like this. And this was computing in the 50s, 60s, 70s. In the 80s and 90s, we evolved into, you know, this type of desktop computer. And then into the 2000s and 2010s and 2020s that we're in now, we're kind of sitting in this space of computing, you know, much more powerful machines. But there's kind of a new class of hardware that's been emerging over the past 10 years or so, right? But it's these types of devices. And just like I mentioned before, you know, this is every bit as much a computer as my laptop computer, or even this computer that's filling a giant room here, right? It's got persistent storage, it's got memory, CPU, and input-output devices, much as your Alexa does, right? It has some persistent storage that keeps the Alexa operating system on there and stores some user information about you. It's got memory and CPU to be able to process and respond to your voice commands and play memory that it's play music and things that it's streaming off the internet through its I/O capabilities, its network connectivity. So yeah, I think your Alexa also would be a computer, as would many Internet of Things devices like a smart thermostat, a Nest thermostat, or a smart fridge, or a self-driving car, or a smart TV that we're streaming YouTube or Netflix or Hulu or whatever on, or your smart doorbell that has the camera that can send a picture and a notification to your phone when someone rings it, Apple Watch, all of these things, I think we could consider computers. Billions of computers in the world. But I'm going to challenge you now a little bit on maybe not the definition of a computer, but what we need to consider a computer, because really most of our computing isn't taking place on this device. Mostly the computing that's taking place on your cell phone or your Alexa or your watch or your TV, most of the computing that's taking place there is really just the display layer, the presentation layer. It's getting data from somewhere else, and it's just displaying the output of computing that's being that's happening somewhere else. The heavy lifting is happening in some centralized location. So it's really now starting to sound a lot like our mainframe days, where we had a big computer that had multiple dumb terminals or screens connected to it. And so these are all basically just screens that are connected to some big centralized computer. But it doesn't look like this anymore. It's not like refrigerator-sized boxes in a room anymore. This centralized computer looks a lot more like this, right? This is a cloud data center, right? So this is the AWS, the Amazon AWS US East region. So anytime you do anything on your cell phone, there's a very good chance that data is being sent to some cloud provider like AWS. There's a lot of processing that's happening in one of these buildings. And then just the result of that query is being sent back to you for your phone to display. Okay. So what's happening in these buildings here? So I mentioned this is the AWS US East region, and AWS has 25 regions spread around the world in different cities, right? So these are spread all around, so you're never very far from an AWS data center. And Amazon doesn't make public details about how many computers they have and what their network throughput and processing capability and things like that are. They don't make that public directly. However, they do have a lot of presentations at conferences where they have engineers who have developed all this talking in broad terms about what their capabilities are. So from things I've watched, I've kind of pieced together a little bit that there are across these 25 regions, 81 what they call availability zones. And each one of these buildings would be considered an availability zone. And an availability zone is typically made up of between 100 and 300,000 computers. Okay, so each one of these buildings has somewhere between 100,000 and 300,000 computers. AWS is made up of 81 buildings, kind of like this. So if you do the math at the low end, if all 81 availability zones have 100,000 servers, that means AWS is made up of about 8.1 million individual servers, or at the high end, up to about 24.3 million servers that make up the AWS cloud. But these don't act as individual computers, right? Because if you go to do something in AWS, you want to deploy a new application or a database or some type of processing engine, you don't get to specify, I want this individual server. This is the one I want to use. Rather, these 8 to 24 million machines are all kind of clustered together into larger chunks and all kind of work almost as one almost infinitely large computer, right? When you send a query to AWS, you just send it to AWS and then it chops it up and distributes it however it thinks would be best across all of these millions and millions of machines. So it's really almost like AWS is just one giant computer, right? One worldwide computer, right? And there are just a handful of these, right? There's the Amazon AWS computer and the Microsoft Azure computer and the Google Cloud computer. And there's a handful of other cloud providers, right? But it's actually kind of back to this realm of about 5 computers that service almost all of our processing needs in the world that are doing the heavy lifting. And these are 5 computers that are made up of hundreds of millions of individual computers, right? And we're connecting to them using billions of individual devices, which are computers in themselves, but they're really just screens. They're really just interfaces that are allowing us to interact with these giant world computers of Amazon AWS, Microsoft Azure, Google Cloud, and others. And I have to give special credit here to a gentleman named Scott Hanselman, who really very clearly elucidated this idea. And if you want to dig deeper into this, I would strongly recommend Googling or looking up on YouTube some of his content, because he does a really great job of explaining some very in-depth and technical computer concepts in a very understandable way. So, check him out. So these 5
sounds great. Could you type that in chat?
Oh, what's that?
Oh, I'm sorry. I said, could you type that name in chat, please?
Oh yeah, sure. It's Scott Hanselman. There we go. Yeah, so check him out. He's a really nice watch. So one of the really great things about these giant world computers is it gives you, right? It gives all of us, just everyday people, access to millions of high performance computers at what is really a very low price, right? So you can go to AWS and for, just a few cents per hour, like sometimes less than 10 cents per hour, deploy a very capable server that's running in the cloud, right? That can be just for you, that can be publicly accessible, that you can write an application and deploy it on there, right? Or if you're using some of their other serverless technologies, it can be even less expensive than that. So you have a lot of resources at your disposal at a very affordable price. And this is in stark contrast to how the world was, again, 25 years ago, or really just about 10 years ago, in that there's no upfront cost whatsoever to being able to do this. Back in the late 90s, I had a little business venture that I was working on, that we had to buy server hardware, which I actually bought secondhand from my employer, but I had to buy this hardware for like $2,000. And we had to have it at a hosting facility that we paid about $100 a month for, to run a website that we used as like a landing page that people would use as their homepage. And we sold advertisements and stuff like that on there. But there was an upfront cost of buying the hardware, and it was fairly expensive on a month-to-month basis, right? So there was that upfront cost. And here's the real kicker. If that website had become insanely popular, and we went from having a few hundred users up to a few thousand or a few million users, my poor server wouldn't have been able to stand it, right? And I would have had to have more hardware outlay in order to meet that demand. That's not the case with cloud computing, because we can just with a few clicks scale this up. And the only limit functionally to how large you can scale is how much money you're willing to pay, right? So we can scale up infinitely if things start going really well. And if things don't go so well, we can easily tear something down. We can just shut these computers down and stop paying for them, right? We don't have to depreciate our hardware and sell it and get rid of it and things like that. So it's a much lower risk to trying out something cool. So a lot of great opportunities there, which kind of leads me into my closing here and a couple of tips for you. And I think some of the great things you can do, just find a way to get involved with computing. And just by virtue of being in this computer organization, I think that's a great start. But talk to the people that work at the help desk. Is there anything that you can help out with there? Kind of learn from being around them. Go to hackathons or to user groups and just kind of see what other people are doing. Get involved with the community, and very importantly, on top of that, ask questions, ask for explanations, and ask what things are doing. And if you're interacting with someone who's very passionate about what they're doing, I think you'll find that they are more than willing, in fact, even excited to explain to you what exactly is happening. And throughout all of my learning, right, my undergraduate degree, my master's degree, my PhD, all of my best learning has come not from this formal academic setting, but it's come from sitting down with a coworker and kind of looking over their shoulder and seeing them do something cool and go, whoa, wait, what is that thing you just did? What did you just click on? Or what was that script you just ran? What is that programming language you're using, right? And that can take you down a whole rabbit hole of new things to learn about. So ask people what they're doing, ask for an explanation of what's happening, and learn that way. Build things, right? And I know I've heard about what you guys have been doing in your group so far, and it sounds like building things is something you're all interested in, with I think designing circuits and things like that. All the resources you have now with AWS and 3D printing and rapid fabrication stuff like Arduino and Raspberry Pi, so many ways that you can rapidly prototype and build kind of new and innovative things. By doing that, aside from the learning you get from that, you're sending a signal to future employers and universities that you're interested in and things like that, that this isn't just an academic exercise for you. This isn't just something you have to do. This is something you're interested in, right? And you've kind of gone above and beyond to create some project on your own. So that's a signal I always look for. And then leverage all the online resources you have. YouTube has a tremendous amount of content. I already mentioned Scott Hanselman, and I've got a bunch of great content out on YouTube. If you Google Professor Mark Grimes, you can find some college level data management courses out there. Things like Coursera, Udacity, Khan Academy. I currently review a lot of applications for our master's in MIS program. And one of the things that always sticks out to me as being an applicant that I really want to get into the program is when they have not necessarily a background in information systems, right? So we get a lot of people that did an undergrad in MIS or an undergrad in computer science, and they'll do fine. The people I really get interested in are people that have a background in marketing or accounting or whatever unrelated to IS, but they've done a certificate in Python programming on Coursera, right? Or they've done some kind of SQL data management course or something. That demonstrates to me a self-motivated drive and passion to understand this. So take advantage of all those resources that are out there. And I know we're running up now on the 3:30 time frame, so I don't know if we're about to be kicked out of the room, but I would definitely be willing to address any questions or thoughts anyone might have if there's any of that in the room and we have time.
Well, sure. I've got to say, that was a really great presentation, and talking to some people over here, from what I heard, we really appreciated that. And let's see, one of the boys had to go, so he gave me a question or two to ask before he left, and then there's some other people with questions. So I guess sort of to get started. So I guess looking more at the software side, how is this going to impact programs in the future as the hardware, continues to improve?
Great question. And I think even more than the hardware improving is just that we now in this kind of massively distributed space, we have to think about writing programs in a little bit different ways. So the old school way of thinking of having a complete program that executes in a procedural way. So that's been kind of overthrown by object-oriented programming. But now if you're thinking about writing a program that's going to be executed not just on one computer, but it's going to be executed maybe on 100 computers, and the results of each individual piece of the portion or of the program aggregated back together, you have to start thinking about writing programs in a way that they can be distributed. And the other big change that we're looking at there is the idea of, instead of single monolithic programs, using what we call microservices. So instead of one program that does 100 small functions, you have the individual small functions set up as microservices, and then other programs or other services can invoke all of these kind of smaller features. And we might do that using something like Amazon's AWS Lambda, for example. Oh, maybe muted.
Oh, shoot. No, I was muted. I just realized that I had a sign pop up that said, "You are muted now." And I was like, let's see. Well, it seems like Jack has a question or two that he wants to ask. He was texting me about. And so if you need a few seconds there, I have Hayden has some more questions, but without anything to do, Jack, would you like to ask anything? Or never mind. He just texted me that he has that he's having some connection problems right now. Oh. So I'm sure he'll be back here in a second. But just a question from Hayden here. So how will people control and prevent from hacking computers in everyday devices like appliances? Because, at the end of the day, if someone puts a virus on your computer, that's bad enough and that's that. But, what do you do when your Amazon smart home decides that, it's not going to let you out of the house until you give them money or ransom or, there's a million similar uses. How do you think that's going to change the world around us?
Yeah, that's a great question. And 20 some years ago, security was kind of not really the first thing that people thought about. And so many of our security concepts, security concepts are kind of bolted on, right? It's this idea of adding passwords to things and adding access control lists and things like that. More recently, we've started thinking about security first, right? You design something with security in mind, and also security in layers, right? So you have security within the application, and you have security at the operating system, you have security at the network layer, so that you kind of have multiple lines of defense. But this is definitely something that is worth considering and worth being concerned about, because we've seen a lot of ransomware attacks and things like that over the past couple of years. So that's one, I think, very good area for aspiring IT professionals to be looking at is cybersecurity, because there is a tremendous need for and lack of good cybersecurity professionals in the U.S. and really worldwide today. So it's always kind of a cat and mouse game between the good guys and the bad guys.
Well, that's definitely a whole lot to think about. And just looking over here, he had to go catch a train because he lives out on Long Island or whatnot. But and so he couldn't connect from there. But he texted me the question, so I'll ask it anyway. So, what do you think about where virtual reality and augmented reality are going, and how that's going to increase the amount of tech, hardware, and software, in our everyday lives even further? Do you see that being a big thing? I mean, it's very hard for us to predict the future, but it seems to have some promise.
Yeah, that's interesting, and I don't know if I'm, you guys may be more qualified to answer this question than I am. From a technology perspective, I think our hardware and software is going to be able to envision, and maybe you're kind of thinking about the metaverse that Mark Zuckerberg announced or demonstrated a couple of weeks ago. I think from a technology perspective, that's something that is within reach, right? Especially because you think about these VR devices, they're effectively just screens, right? They're screens that are going to be connecting up to this giant processing facility, one of our 5 or so world computers. Now, personally and socially for me, I look at the metaverse and I go, wow, I'd actually much rather just hang out with my friends on the back porch and play like a real live game of ping pong or sit around a real campfire. But social dynamics change a lot, right? And things that I do socially and behaviorally are very foreign to my parents' generation, right? And also very foreign to your generation, this emerging generation. So I think there's probably a strong possibility that things like that do continue to materialize, and this idea of having living a maybe non-trivial amount of your life in some avatar-based virtual world thing, like maybe that will be a thing. But like you said, it's very hard to predict.
Well, yeah, thank you so much. It appears he's back on the call. If there was anything that, Jack, are you there? Anyway, I'm so sorry about that. He had like I was saying before, the train's a little spotty, but it's been great having you here. And It's just been wonderful to see you again, Uncle Mark. And yeah, do you have time for another question or two, or what does your schedule look like? Because anything's totally fine, and this has been totally wonderful.
Yeah, sure. Yeah, I'm happy to spend another couple of minutes if there's something you guys want to talk, or of course you or anyone else really welcome to reach out to me. Oh, I realize I don't have my contact information here, but if you Google me, you can find me pretty easily. So.
Oh, sure. Well, that's quite all right. If you'd like, you can put that contact information in chat, and I'll copy and paste it and send it out in an email. So that's very doable. But I guess just to sort of wrap it up with one more concrete question about uh, practical things going forward is what advice do you have for people that are considering careers in computers? And what skills and areas of knowledge would you suggest building up now so that you can be ready either, as an undergrad or as doing grad or PhD school, or you just getting a job somewhere in the computer world right now?
Yeah, I think the things that I had mentioned before, as far as, getting involved with anyone you can find that's in the tech space, right? Be it your help desk at the school or a repair shop or a user group or a hackathon, something like that, and asking questions and letting, and learning from people that are doing it. As far as specific areas that I think there's going to be a lot of growth in, cybersecurity definitely one of them, but data management being the other. And that's mostly what I teach here at the University of Houston, because the amount of data that companies are using, people have been talking for years now about this idea of big data, right? But we haven't really been doing big data, and we're still not really doing big data, right? It's kind of a buzzwordy thing right now, and we're just getting on the verge of companies really understanding the power of data, right? And how to collect large amounts of data and how to analyze it. So, to get the basic ropes of data management, looking at things like structured query language or SQL for interacting with relational databases. That's been the core of business data management since the 70s, or at least since the 80s. It was developed in the 70s and is still very fundamental to most business problems. But now we have emerging classes of database called non-relational databases that allow us to work with big data more effectively and more efficiently. So starting with SQL or SQL and then learning about other data management methodologies, I think is a really good way to get started, kind of understanding how to wrangle data, how to analyze data. I really appreciate you having me here. It's been neat to get to share this with aspiring technologists. And again, I'm happy to be in contact at any point, and wish you guys all the best.
Well, thank you so much. We've really enjoyed having you here, and we can't wait to put a lot of these ideas to work later on in the year, and we'll keep you posted when we start working on electronics projects.
Awesome. Very cool. Well, you guys have a great rest of your day and go forth and do great things. And I look forward to seeing and hearing about all the great things y'all are going to do.